So antidifferentiation, the opposite of taking the derivative or the reverse process. And notice what we're doing. We're starting with a derivative and we're trying to figure out, hey, if we know this is dy dx, what was y? If this is f prime of x, what was f of x? Okay? So you see here, we can often figure out what a rate of change is. But how would we take that rate of change and translate that into a model? Okay? So, here's kind of a visual for us. When we have y, or f of x, and we differentiate, or we take the derivative, we get dy dx, or f prime of x. If we take the integral of that, that will get us back to the y. Okay? Now, this is a general trend. As we'll see here, this is not exactly an inverse relationship, because what has to be true about an inverse relationship? Do you guys remember inverse functions? That's one example. That was more the perpendicular. Inverse functions. Okay, it always has to be true. You know, in other words, if I take f of x and I get a value, and then I take the inverse function of that value, I should get right back where? To where you started. Okay? Remember, we called those functions, in order to have an inverse, we said they had to be 1-to-1. Okay? This process is a reverse process. However, one thing we'll see here is that when we take the integral, there actually can be more than one function that will give us the same derivative. Okay? And it'll make total sense to you once you see it. You can get the same derivative from many different functions. For example, everyone, on your paper, write down a function that has a derivative equal to 3. All right, so we have one?
Y equals 3x.
Okay, so we came up with y equals 3x. All right, what else? 3x plus 1. Any others? 3x plus 2. 3x plus anything, right? Right? So here's the thing. All of these have a derivative of 3. Okay? So if I were taking the integral of 3, I could theoretically have 3x, or 3x plus 1, or 3x plus 2, or 3x plus anything. And that actually is kind of the difference between, remember we mentioned earlier, the definite integral, where we were going from a to b? When we do that, that anything doesn't matter. It'll all cancel out, so you don't have to worry about it. And I know that doesn't make sense right now, but we'll talk about it really soon. Okay? However, when we're doing what's called the indefinite integral, in other words, we just want an expression, not a particular interval. In that case, we will actually put what's called the constant of integration. We use a capital C to represent, it could be any real number, any constant. So 3x plus any constant will be the integral or the antiderivative of 3. Okay? Yes?
How?
What?
How? Because all of those all of the b's
Mm-hmm.
are going to transform the function.
Yes.
So if you take the derivative, it doesn't matter because the derivative is 3, and like you can find the derivative at a certain point. But like the area is going to increase when you have different. Like the area is going to change when you have different b's.
It will.
So then why do you not care about the b?
Well, we'll see. We'll see later.
Sir, I have an interview with the college right now, like in 5 minutes. Can I go to the library, please?
Okay.
Please give me the pass.
Yeah. Okay, so for right now, you kind of just have to trust me on this one. All right. We will look at why this works, exactly how this works. It actually goes down to what's called the fundamental theorem of calculus when we're defining definite
So I
integrals.
wasn't supposed to understand what you just put up for with the c.
Not completely, but I mean, you should understand that it can be anything. Okay?
Integrate stuff for now, just put a C on if it's in depth.
So, yeah, basically right now, if you're not doing an exact interval from A to B, you just do the integral and you'll put a little plus C at the end. Okay? All right, so here's what we have. Here's the concept we're dealing with. All right? If capital F of x is a function where its derivative is f of x, we say the derivative of capital F of x is f of x, and the antiderivative of f of x is capital F of x. Okay? So here we have this notation. This is common notation. Use capital F of x for the antiderivative of f of x. If we had g of x, we'd use a capital G of x. All right? Using that capital notation. So kind of along the same lines as what we had over here, if we're looking at a function, all right, f of x equals 3x plus 5, the derivative of that is 3. We could call the 3 our original function. F of x, capital F of x, would be the antiderivative of 3. Okay? And as you can see, we've already looked at, it can be 3x plus any constant. Okay. Now, I want to think through a few of these logically here and see if we can't, figure out what the derivative or the antiderivatives of these would be. Okay? So I'm having to type everything. So let's start with x cubed. Okay? We got x cubed. All right, we'll do that one in green. All right, so over here, x cubed. Now I want you to think about this. If I were doing this and I wanted, here we go, my text to be green, okay? If I wanted my antiderivative, or I'm sorry, I wanted my function to equal x cubed, what am I going to take? That means the derivative is x cubed.
Wait, why is your capital F prime? Why wouldn't it be your little f prime equals big F?
No.
Like I don't understand why.
Capital F prime
Is the integral.
is the function we're trying to integrate. Okay? So we're trying to figure out
Well, we're working backwards.
we're working backwards. So what would the original function be? Original function. There we go. Now that I can spell. What would that be? Let's think about it. How would I get an x cubed if I was taking the derivative? the function I took the derivative of would have been x to the fourth, okay? So let's try that. The derivative of x to the fourth equals what?
4x to the third.
4x to the third. Now, is that exactly what I'm looking for? No, but it's close, right? What would I have to do to this?
You take the second part by 4.
I'd have to divide it by 4, okay? So let's think about this. If I can do this, and let's say I make it 1/4 of x to the fourth, the derivative there would be 4x cubed divided by 4, right?
Yeah, that's cute.
So now I have what I'm looking for. It's just x cubed.
Oh, so it's literally just coming up with something and then getting.
So it's usually going to be manipulating it. You're probably not going to get like the actual.
No, you will get the actual derivative, the actual integral, capital F of x, the antiderivative of x cubed is what we just found right here. 1/4 x to the fourth.
You know what I'm saying? You're never like, it'd be rare that you, like if our derivative was 4x to the third, like usually you're gonna have to manipulate it. Here, that works fine. Yeah, I'll just go with that.
Well, here's the thing. You're not going to be able to just logically figure out all of these, okay? I'm doing this with ones that we can logically figure out so that we can eventually develop some rules, okay? And that's where we'll then use the rules. We won't just kind of go through this whole process. But I want you to understand the process, the thought process here that we're using, okay?
Yeah.
So, all right, so that's our first one, x cubed, okay? And this is the antiderivative because its derivative equals what we were looking for, or what we started with, okay? Now, let's try another one. Let's go with e to the 2x, okay? E to the 2x. I'm going to put this one here. Okay? So, the derivative of the antiderivative is our f of x, which is e to the 2x. Okay? So let's think about what we know.
The original still had to be, it had to be e to the 2x.
Okay, let's think about this. If I took the derivative of e to the 2x,
It'd be
what does
2
that
e to the
equal?
2x.
It's 2e to the 2x.
So 1/2 e to the 2x.
There we go. Therefore, if I throw in a 1/2, if I do e to the 2x, but then I divide that by 2, that'll give me 2e to the 2x divided by 2. And the 2's will cancel out. That equals e to the 2x. Okay? So, what is the antiderivative?
1/2 e to the 2x.
1/2 e to the 2x. I don't like how that looks. Okay, 1/2 e to the 2x. So 1/2 e to the 2x is our antiderivative. That's it. Thanks. All right, does that make sense? All right, pretty logical. Can figure that one out. Eventually, we're going to use some of these observations to then develop some rules, okay? Last one here. We'll go with blue on this one. Oops, what happened here? There we go. Okay, so let's think this one through. We've got,
X to the negative 1/2.
yeah, we've got the derivative of our antiderivative In other words, our original function equal to x to the negative 1/2. Okay, so again, let's think with me here.
So you would have to have x to the second power? No. You know what I mean? Like, would you have to take -1, so x to the 1/2.
You would have to have an x to the 1/2. So if I have x to the 1/2, what's the derivative? Whoop, I shouldn't have equals yet. What's the derivative of that? -1/2 x to the negative 1/2, right?
So just 1/2.
All right, and it's running into this, I know. Let me get this out of the way.
So it's just 1/2 x to the negative 1/2. No. Yeah.
What would we do with this?
Have your calculator do it.
If you divide it
Wait,
by
what? Hang on. Yeah, since it ends up being divided by 2, if I make it a 2x to the 1/2, then when I get this, it's multiplied by 2. 2 times that, okay? And the 2 times the 1/2 cancels out, and I've got just the x to the negative 1/2 that I was looking for. So, what is my antiderivative? 2x to the 1/2. Okay? 2x to the 1/2. So, here's some kind of ideas here that you may be able to start to see a pattern or two. But remember, are these the only functions that could be the antiderivative? No. We could have the plus c. Okay, let's throw in that plus c. So over here, it's going to be plus c. All right? And then that's going to be on all of them. All right? So we're going to have one over here. And we're going to have another one over here as well. Okay? So, that's a little bit of a mess, but you got the idea. All right? All right. Number 1, this is the only one I want you to try. So number 1 on the previous page, number 1 on this page. Use some logic and it has 7 parts, 8 parts. Come on, you guys can figure this out. I know you can.